So now we'll move to other techniques of characterization, but after associating the graft or ungraft fibers or nanoparticles with a polymeric matrix. So, of course, the test to be performed depends on the target application. I will show you some experimental techniques that can be used, the most used techniques. To assess the morphology, usually scanning electron microscopy is used. It's also important to test the adhesion between the fiber and the matrix. So, tensile test, water uptake, dynamic mechanical analysis, DSC that we already mentioned this morning, and gas permeability. So, scanning electron microscopy. A scanning electron microscope is a type of electron microscope that produces image of a sample by scanning the surface with a focused beam of electrons. The electrons interact with atoms from the sample, producing various signals that contain information about the surface topography. So, of course, it's important for the specimen or for the sample to be examined to be conductive. And also, it's important to have a brittle surface because usually the thickness of the sample is observed, so the facies of rupture is observed, and it's necessary to have a brittle fracture to avoid any plastic deformation that can induce some wrong information. For this, it's necessary to dip the material in liquid nitrogen, so at very low temperature, and to break the sample at this temperature to be sure to have a brittle fracture. Then after fracture, the sample is mounted. It is coated with an electrically conducting metal, so it can be gold, palladium, silver, chromium, other thing, onto the non-conducting specimen, which is called sputter coating. So, you have here some examples of the facies of rupture of composites. In this case, so it's not indicated, but the matrix was polypropylene, and the fibers were wood fibers, and so untreated fibers, and in this case, fibers were coated with maleic anhydride polypropylene, so a random copolymer that promotes some interfacial adhesion. Usually, when the adhesion between the fiber and the matrix is poor, we can see two things. The first thing is a gap or a void at the level of the interface. Of course, you imagine that in this condition, the stress transfer of the interface is very poor, meaning that we cannot expect good mechanical properties. When increasing or when improving the adhesion, for example, with this copolymer, we cannot see anymore this void, meaning that the adhesion has been improved. This is another example with banana fibers, also in polypropylene. So untreated fibers, we can see again this void. This is the fiber, this is the matrix. And after grafting or after applying this copolymer, this is the fiber, and you can see that there is no more void. The adhesion has been much improved. So this void is an indication of the absence of adhesion. There is another thing, which is here. You can see here a fiber which is out of the surface. This phenomenon is called pull out. When breaking the sample, if there is no adhesion, the fiber can slip in the matrix. So, these are some other examples. I don't remember which kind of fiber, but so it's a natural fiber. I don't remember the matrix also, but what is important is, again, this gap at the interface and an improved compatibility or improved adhesion after treatment. We have already seen this micrograph. I think it was yesterday or 2 days ago, I don't know, with PLA and PLA plus 5% cellulose nanocrystals with this big aggregate and again this gap or this void at the interface. And after compatibilization, following these two strategies, we cannot see anymore any aggregate. So remember that with scanning electron microscopy, we can see microscopic fibers, but we cannot see these nanoparticles. We can only see if there are aggregates or not. And so this is AFM, so it's not SEM. And again, without modification, this big aggregate here of cellulose nanocrystals and no more aggregate after grafting, in this case, polycaprolactone on the surface of the nanocrystals. So, adhesion test. This is called micromechanical characterization. There are mainly two techniques or micromechanical tests to assess the quality of the adhesion between the fiber and the matrix. The first one is called pull-out test. In this test, one end of the fiber is embedded in a block of the material which is a matrix, and a force is applied to the free end to pull it out of the matrix, while the force is continually monitored and recorded. You can see here, we can see one end of the fiber, which is embedded in the matrix. A force is applied, and the objective is to extract the fiber. And of course, you can imagine that if the adhesion is good, the force to extract the fiber should be higher. From this experiment, and this is another way to perform this experiment. You can see here the fiber, here a droplet of the polymeric matrix with a hole, and so the fiber is extracted from the matrix. From this test, the average interfacial shear stress can be calculated from this force, at which debonding occurs using this equation. So tau is the interfacial shear stress, F is the force necessary to extract the fiber, D corresponds to the diameter of the fiber, and L is not the length of the fiber, but the length of the fiber which is embedded, of course, in the matrix. This is another test. Maybe I will explain this later, which is called the single fiber fragmentation test. In this test, a single fiber is embedded in a dog bone-shaped tensile specimen that will be submitted to a tensile test. Tensile tests are transferred from the matrix to the fiber, and depending on the level of fiber matrix adhesion, tensile stress builds up in the fiber. The fiber tensile stress is reached at some point where the stress concentration is high enough for it to fracture, and the loading process continues until the fiber fragment lengths are too small, so small that tensile stress induced in the fiber can no longer reach the fiber tensile strength and the fiber fragmentation process, CIS. Briefly, you have the fiber, which is embedded here in the matrix. A tensile test is performed. You can have two different situations. If there is no adhesion between the fiber and the matrix, when performing the tensile test, of course, the strength or the modulus of the fiber is higher than the one of the matrix, but the material, the fiber, is usually more brittle, meaning that it will break first. Now, if there is no adhesion, you can imagine that after this break locally of the fiber can slip in the matrix if there is no adhesion. Meaning that if we have only two pieces after fracture, it means that the adhesion is poor. On the contrary, if there are much more pieces of the fiber, it means that the adhesion is increased. So, after this test, the objective is to count the number of pieces of fibers. When using a transparent polymer matrix, it's quite easy. an amorphous polymer. But when it's an opaque fiber, polymer, it's necessary to polish the sample up to reaching the fiber. Okay? So the reason for this is report here. When a fiber, which is embedded in a matrix, is subject to a tensile force. There are two types of stress that apply to the fiber. At both ends of the fibers, we have a high shear stress, which is applied, but in the middle of the fibers, the shear stress is zero. There is also a tensile stress, which is applied to the material, mainly on the main part of the fiber, but not at the end of the fiber. So it means that during the tensile test, the fiber will break when it reaches the stress at break, or the strength of the fiber. And this depends on the length of the fiber. Because if the fiber is too short, this is this stress, tensile stress in the fiber. If the fiber is too short, it will not reach this stress at break of the fiber, meaning that you cannot benefit from the mechanical properties of the fiber. On the contrary, by increasing the length, we can reach the strength at break, or stress at break of the fiber, and then we can benefit from the mechanical properties of the fiber. So it means that it's necessary for the fiber to have a length which is higher than this critical length. So, the final fiber fragment length is referred to as the called critical length. The fiber critical length is a good indicator of the ability of the interface to transmit loads between the two constituents, and the ratio of the critical length divided by the diameter of the matrix can be used as an indicator of the fiber matrix bond strength. And we calculate, as previously, the interfacial shear stress using this strength of the fiber, stress at break of the fiber, and this critical length. So this is the same information which is a report. One important thing is that, so to process composite, we have seen that there are different techniques. For thermoplastic, what is mainly used is melt blending, so it can be also extrusion or injection molding, and in this process, high shear rate are applied. When considering glass fibers, usually the length of the fibers decrease during melt processing. When considering natural fibers, these fibers are more flexible, meaning that we can keep the aspect ratio or the length of the fiber. So typically for high performance short fiber composite, it's necessary to have an aspect ratio that is at least 100. So tensile test, of course I imagine that you know tensile test. It's a fundamental materials engineering and science test in which a sample is subject to a controlled tension under a constant stretching rate up to the fracture of the sample. So there are two holding grips. This one is fixed. This one is moving to the top for a tensile test, to the back for a compression test, of course, at a given speed. And there is a load cell here to record the force which is applied to the material. So meaning that in this test, we have the force applied to the material as a function of its elongation. So you know that usually we don't use this raw data, but what is used is the force is converted into a stress, meaning that the stress, the force, sorry, is normalized to a given section, and the elongation is converted into strain. How do you define the stress? The stress, sigma, is a ratio of the force divided by the section of the sample. Okay, so it means that it's in Newton per square meter or in Pascal. There are two types of stress that can be used. S0 here refers to the initial section of the sample. Imagine a sample in the form of a cylinder. So when applying the force, and if the deformation of the sample is high, of course, the section of the sample will decrease. So it means that we can consider only the initial section of the sample, which is easier to determine. In this case, this stress is referred to a conventional stress, or we can use the actual section of the sample, meaning that it's necessary to follow the evolution of the section of the sample during the test. And this stress is referred to as true stress. But usually, this conventional or nominal stress is used. But you understand that for rubber, there is a big difference between these two values. Now, the strain. How do you define the strain? Please tell me, because I'm sure that you will be wrong. I'm sure that you want to tell me the ratio of the elongation divided by the initial length. No? No. It's not this. The strain is defined by this equation. It is the logarithm of the actual length divided by the initial length. So this is the initial length before applying the force, and then it increases when applying the force, and it decreases for a compression test, of course. This is the definition of the strain. Of course, the actual length is L0, the initial length, plus the elongation. Okay? This is the true strain. Now for low elongation, or what we call the linear range. If delta L is weak, we can develop this expression. In this case, it is this expression, what you expect probably. But again, you can imagine, so this is the nominal strain, and this is the true strain. Again, you imagine that for rubber, for which the elongation is very high, the difference is very high also. So, typically this kind of curve is obtained. So the stress is a function of strain. We have first a linear behavior. Linear behavior meaning that we have a linear relationship between the stress and the strain, and of course, the parameters that link the stress and the strain is the modulus. Then we can see that there is a loss in the linearity of the curve, meaning that we are out of the linear range. In fact, this is not really the linear range, because the linear range is defined for strain which are lower than 0.1% Here it's much higher. But anyway, this is the reason why the modulus determined by tensile test and the modulus determined by dynamic mechanical analysis is different. So, loss of linearity, then there is a maximum in the stress, which is called the yield point, or yield stress. And then there is a phenomenon which is known as necking. So this is not for all materials. For example, in the case of polystyrene, we have a brittle fracture, meaning that the fracture occurs in the linear range. But this is for most polymers. This necking corresponds in the local decrease in the section of the sample. We'll show a video on this. This is due, of course, to an alignment of the macromolecule. And then we have a strain that occurs with a more or less constant stress, and then we have an increase in the stress up to the break of the sample. So it means that from this curve, we can determine the initial slope, the modulus, of course, the yield strength, which is important because from this deformation, we don't have anymore, so at the beginning it's an elastic deformation, then after the loss of linearity, it's a viscoelastic deformation, and from the yield point, we have a viscoplastic deformation. So plastic deformation means that we have irreversibility of the deformation. And of course, we can determine the strain at break and the stress at break. Another information that can be obtained from this curve is from the area under the curve. The area under the curve corresponds to the energy of fracture of the material. Yes, so you can see here a stress-strain curve with this necking that developed from the yield point, and then you can see that the necking or the thickening of the sample, thinning of the sample, is propagated along the whole sample, and this is due to some alignment. We will see a short video that shows a tensile test performed on high-density polyethylene. So this is the tensile test machine with the sample, the upper grip, the lower grip, of course. We will see also, maybe later. Yes, here, what is called an extensometer. Extensometer allows to determine only the deformation where the sample has a constant section. So, the test start. You will see locally, I think it should be around here, the necking, and in the region where the necking occurs, we can see, yes, here we can see that there is a slight change in the color of the sample. It is becoming whiter. The reason for this is that we have an alignment of the macromolecule, meaning that the refractive index of the material is different. And so, then the necking propagates along the sample, and of course, at the end, the material is broken. The material is broken, and you will see a lot of small fibrils, which is characteristic of a subicrystalline polymer. Yes, here. Yes, and this is the curve which is obtained. Of course, it's important to control the parameters that you use during this test in order to be able to compare your data to the literature. The shape of the curve and then the parameters that you can extract from this curve depend on the temperature at which the test is performed. Usually it is room temperature, but it can be changed, of course. For high temperature, usually the modulus is lower, of course, but the material is more deformable. So the elongation at break is higher. And when decreasing the temperature, progressively we pass from a ductile material to a brittle material. So it means that it's difficult to say that the material is a brittle or ductile. It depends on the temperature at which the test has been performed. Another parameter which is important is the strain rate, or the rate of elongation. If the test is performed with a slow elongation rate, usually the modulus is lower and the elongation at break is higher. But when the test is performed with a high elongation rate, the modulus is higher and the strain at break, or the material is more brittle. Okay, so it means that it's very important to control this parameter. For example, in the case of polypropylene, when performing the test at room temperature at 10 millimeter per minute, which is classically used, we have a high deformation at break with a necking. If the test is performed at 200 millimeter per minute, we have a brittle fracture. So these are just some examples of stress strain curves in which glycerol plasticized corn starch was reinforced with cotton filter waste. And so what we can see is that when adding the fiber, or the cotton in this case, usually the modulus increases, so it corresponds to the initial slope of the curve, but the material becomes more brittle. Usually, but not always, it depends, the strength, the stress at break can increase, and usually the curve under the area, under the curve decreases, meaning that for composites, the energy or the breaking energy is decreases. So these are some other examples. You have here it's a function of fiber weight fraction. I don't remember. Yes, it's low density polyethylene, sorry, with cellulose fibers. So elongation at break, it decreases when the material becomes more brittle when adding the fibers. Regarding the modulus, we have an increase here and also an increase in the strength in this case, which is not always the case. An important parameter, of course, is the compatibilization between the fiber and the matrix. You have some example here for the modulus and for the strength. The same sample without any chemical modification of the fibers and with chemical modification using this silane agent. And what we obtain generally is an increase in the modulus and an increase in the strength. But when increasing the adhesion between the fiber and the matrix, the stiffness, the modulus and the strength of the material usually increase, but the elongation at break decreases. So this is another mechanical test that can be used. It's called impact test. Do you know Sharpie test? Have you heard about this? Yes? No? Okay. It's a very simple test. It's a standard test. This is the principle. It's a measurement of the residual energy of a mass in pendulum movement that caused by a single impact at a given speed and energies a rupture of a given size test. So it's a standardized high strain rate test which determines the amount of energy absorbed by a material to fracture. You have here what is called a hammer. This hammer has a given potential energy. It depends on its weight, of course, and it depends also on this height. The hammer is released. The sample is here. You can see that it is on two supports. And of course, the hammer can break the sample, and then you have the end of swing, and of course, part of the potential energy is used to break the sample, and from this initial potential energy and this energy at the end of the test, we can determine the energy that was necessary to break the sample. So the problem with this kind of test, and of course the dimension of the specimen are normalized. I don't remember, I think it's 4 millimeter, 10 millimeter for the 8, and 4 centimeter between the two supports, I think. But so the problem is that there is a broad distribution in the result. Because if you have any defect in the sample, it will break at this specific localization. It means that usually a notch is performed on the sample just to localize the break of the sample. And so the distribution in the result is reduced. Another test which is similar is called ISOD. It's exactly the same thing, except that in this case, the material or the sample is clamped on one end, and the hammer will break the sample at the free end, and again, a notch can be used. So, this is for water uptake measurement. So, maybe we can read this. Sample which are thin enough so that the molecular diffusion can be considered as one-dimensional are dry first, cool, and then wait. It gives a mass M0. And then it is immersed in distilled water or stored at a specific relative humidity. For example, if you are using starch, if you immerse starch in water, it will dissolve. So for this, it's better to use a given specific relative humidity. Then the material or the specimen are removed at specific interval. They are blotted to remove excess water on the surface and wait, give this weight, up to equilibrium. Equilibrium corresponds to the stabilization of the weight of the sample. And from that, we can determine the water uptake from this equation. We can also use this equation in which you can see we have the diffusion coefficient of water that can be determined. So you can see this equation is not really friendly. No? So it means that usually another equation is used. I will show you. So in this equation, 2L, where is L? It's here, correspond to the thickness of the film. So D is the diffusion coefficient. But for shorter time, this equation becomes more simple. And usually we use this one. And it is observed that when this parameter is lower than 0.5, the error to determine the diffusion coefficient using this equation instead of this one is of the order of 0.1%. Of course, it's easier to use this one, so it means that you need to use this equation, but only at the beginning of the experiment. So these are some examples of water uptake. So in this case, it's not, yes, it was untreated softwood fibers in polypropylene. So when increasing the amount of cellulose of softwood fibers, of course, the water uptake increases because polypropylene is hydrophobic. So these wood fibers are hydrophilic, and of course, the water uptake increases. On the right side, you have the same curve, but for wood fiber, or softwood fibers that have been coated with the copolymer of malonic anhydride polypropylene. Again, when increasing the amount of the fiber content, the water uptake increases. What is the difference between untreated and treated fibers? Just for you to wake up. I know you can sleep a little bit sometimes. I can't, because otherwise you will see it, of course. What is the difference? Look at the scale. 6%, 2%. of course, the water uptake is much lower for treated fibers. And we can understand because after treatment, after modification, the fibers are less hydrophilic. In addition, remember that for untreated fibers, we have a gap between the fiber and the matrix. And of course, you imagine that this gap can be filled with water, meaning that the water absorbed by the unmodified composite is usually higher. So dynamic mechanical analysis, this is my favorite technique of investigation. So DMA measures the properties of material as they are deformed under periodic stress. So meaning that, for example, in tension, we apply periodic stress to the sample. The magnitude of the deformation is very low. So it is in the linear range, it's below 0.1%. So, of course, by applying this sinusoidal stress, a sinusoidal strain is generated, and depending on the material, the two sinusoids can be in phase or they can be out of phase. For a perfectly elastic material, the two sinusoids are in phase, and for a perfectly viscous liquid, we have a shift of 90 degrees. And of course, for a viscoelastic material, for a polymer, we have a shift between the two sinusoids, and this shift is characterized by an angle, which is generally called delta. Delta is called the damping factor. Sorry, damping coefficient or loss factor. So we determine E prime, which is the elastic or storage modulus, which is associated to the elastic part of the material. E double prime, which is associated to the viscous part of the polymer, which is called the loss modulus, and the ratio between these two moduli correspond to the tangent of this loss factor or loss angle. And so we can determine the evolution of these three parameters. In fact, experimentally, only two are determined. E prime, it is just the stiffness of the material, and delta, or tangent delta, because it corresponds to the shift in the two sinusoids that can be experimentally determined. E double prime is derived from this equation. And so these three parameters can be followed as a function of temperature or as a function of frequency. High frequency, slow frequency. But of course, if this parameter or the evolution of this parameter is followed as a function of temperature, it's necessary to have a fixed frequency. Usually 1 Hertz is used. Or if the experiments are performed at a given temperature, or at a different frequencies, it's necessary to keep the temperature constant. Only one parameter can be changed. So there are different geometries. Single cantilever, you can see that the material is fixed at both ends, and so only one end is moving. Dual cantilever, we have a movement here. Shear, so the material is in gray here, and it is shear. Compression, so the material is compressed, of course. Tension, or torsion can be applied. We can have this different geometry for the test. And so, typically, the curve which are obtained are reported here. So the storage modulus, so in this case, is as a function of temperature, meaning that the frequency is fixed. So the red curve corresponds to the storage modulus. It is the stiffness of the material. At low temperature, the stiffness is high. You can see, typically around 1 gigapascal. Then we have a sharp drop of the storage modulus. The magnitude of the drop of the modulus during this relaxation, which is associated to the glass transition temperature of the polymer, depends on the nature of the polymer. If the polymer is fully amorphous, we have a drop over at least 3 decades. If it is lower, which is the case here, it is a semi-crystalline polymer. Then for the mechanical damping factor, so tangent delta, we have this evolution. We have a maximum in the relaxation zone. In fact, this damping factor represents the fraction of energy which is dissipated in the sample. During this sinusoidal test, so during the first part of the sinusoid, some mechanical energy is provided to the sample, and during the second half cycle, only part of the energy is recovered. And so this loss angle represents the fraction of energy which is lost during the second sample compared to the total energy that was provided during the first half cycle. Okay? And the loss modulus has more or less the same evolution as the loss angle. So these are just some data. I don't know. Sorry. The same curve as a function of temperature for the storage modulus and tangent delta, but you just have here measurements that have been performed at different frequencies. When increasing the frequency of the measurement, the curves are shifted to higher temperature, meaning that if you want to compare your result to result from the literature, so it's important to be in the same condition and to perform the measurement at the same frequency. So this is something which is very specific. Maybe I can describe it briefly. It is for PLA, polylactic acid. One of the characteristics of the PLA is that it's a polymer that I don't like, but this is not important for the curve. Now, another characteristic is that the kinetics of crystallization of PLA is slow. So it means that you know that a semi-crystalline polymer can be obtained as a fully amorphous polymer or low crystallinity polymer by applying what is called a quenching. Quenching is a fast cooling of the polymer from the melt down to a temperature which is below the glass transition temperature of the polymer, because the polymer can only crystallize between Tg and its melting point. In some cases, it's impossible. I take the example of polyethylene, high-density polyethylene. The melting point is 140 degrees. The Tg is very low, so it's maybe minus 100 degrees or something like this. The kinetics of crystallization of polyethylene is very fast. So it means that it's not possible to scan the range from 140 to minus 100 fast enough to avoid the crystallization. But so for some other polymer, it's possible. For example, for PLA, the melting point is around 150 degrees Celsius. The Tg is around 60 degrees Celsius. You have two curves. One that corresponds to PLA that was slow cooled, so meaning that before this experiment, the PLA was cooled from the melt slowly, meaning that the material can crystallize. It will not crystallize at 100%, it's not possible, but it can crystallize to its maximum capacity. That can be 20%, 50%, depends on the polymer. And here you have the same curve for PLA that has been quenched, rapidly cooled. And then we have these two experiments. Of course, during quenching, the material cannot crystallize, or at least it will not crystallize at its maximum capacity. You can see the result. PLA slow cooled, we have this relaxation associated to TG. Then a rubbery plateau much higher than 1 megapascal, which is characteristic of a subcrystalline polymer, and then melting. Now for the quench sample, we have a stronger or sharper modulus drop associated to TG, a lower rubbery plateau, which is associated to a lower degree of crystallinity, but for a given temperature, the material can crystallize and the modulus increase. There are two reasons for which the modulus of a polymer can increase during heating. Crystallization. Another reason can be the loss of a plasticizer. For example, for starch, so it can be plasticized with water, but of course, when heating the polymer, water will evaporate, and because of the loss of plasticizer, the modulus is increased. So DSC, we already discussed this previously. We can observe the TG, crystallization. So exo is up, so crystallization and melting. Of course, from this curve, we can obtain different information. The TG, of course, usually it's the inflection point on this curve. We can determine the maximum of this crystallization peak, correspond to the temperature of crystallization. The temperature, corresponding to the peak, to the melting peak, it is of course the melting temperature. You can see that there is another temperature which is reported here. It corresponds to the intercept between the tangent of the peak and this baseline. It is associated to the beginning of crystallization or beginning of melting, even if you see that melting starts before, but by convention it is like this. And there is another data here, in joule per gram. You know what is this? If you have performed DSC experiments, you should know. Have you performed? It corresponds to the enthalpy of fusion. Okay? Enthalpy of fusion, so it's joule per gram. It corresponds to the energy which is dissipated, in the case of melting, to melt 1 gram of material. And for crystallization, it's an exothermic phenomenon, meaning that it corresponds to the energy which is released per gram of material. In fact, it's not directly related to this curve. Sorry, I'm using the whiteboard because I was hoping to finish my slide, but yesterday I didn't have enough time. Yes, the enthalpy of fusion or of crystallization, which is not like this, so it's in joule per gram. So it corresponds, of course, to the area under the peak A. But what is the unit for the area under the curve? Under the peak, sorry. We have here watt, joule per second. Temperature, Kelvin. So the area under the curve has this unit. It doesn't correspond. In fact, it's necessary to normalize this area to obtain the enthalpy of fusion. You don't need to do this. The software do it directly. Because at the beginning of the experiment, you have to specify the heat rate you are using and the mass of the sample. And in fact, when normalizing this area by the mass, so which is in gram or kilogram, and by the heating rate, which is in Kelvin per second, you can see that at the end you have joule per gram. Okay? But what I want to say with this is that if you compare two thermograms, and if you see that one peak is stronger than the other, you cannot say it is more crystalline. Depends on the heating rate and the mass of the sample. Also, to determine the degree of crystallinity of the sample. The degree of crystallinity, QC, is the ratio of the enthalpy of fusion divided by the enthalpy of fusion of what is called the perfect crystal. Perfect crystal is a 100% crystalline material. It cannot be experimentally determined, of course, but it can be obtained by extrapolation. So this is for a polymer. Now, when using a composite, it's necessary to use this equation, where Wm represents the fraction, the mass fraction of the matrix. Because, of course, only the matrix can melt or can crystallize, not the fiber. And when you determine the enthalpy of fusion, the mass which is here, it is the mass of the composite. Okay? For example, if you have, let's say, 20% fibers, meaning 80% by weight of matrix, Wm will be 0.8. Okay? If you have 30% fibers, 70% matrix, Wm will be 0.7. Okay? Yes, so this is just to show you. I think I will pass the next slide because I remember that we already saw this. DSC thermogram record during heating, so the bottom curve, and cooling, top curve, of banana rashi polypropylene composite. So A corresponds to the neat matrix, B 25% raw fiber, C 50% raw fiber, and for D it's 50% extracted fibers. So different treatments have been done to remove the waxes and so on. So this is heating, this is a melting point. Cooling, so it corresponds, of course, to crystallization. What we can see is that with the fiber, the crystallization occurs at higher temperature compared to the matrix. It just means that the crystallization is easier in the presence of the fiber, which is often the case. And the reason for this, but I will not detail because we discussed this yesterday, I think. Sorry. No, for the next slide. No, I will just discuss this. So this is the same sample and the analysis of the previous curve. The temperature of crystallization, you can see that crystallization occurs at higher temperature for composite. The melting point is the same, and the degree of crystallinity tends to decrease when adding the fiber. So it decreases, just indicates that the presence of the fiber limits the organization of the matrix, and we have this decrease in the temperature of crystallization, which is referred to, we have already seen the nucleating effect of the fibers. And we have already described. You remember? Yes? Okay. I hope so. I think we already seen this. Just to show the nucleating effect of the fibers. In this case, it was natural cellulose nanocrystals that were compatibilized with a matrix, which was polypropylene, using this quaternary salt. And what we have seen is that, in this case, the crystallinity of the matrix increased when adding cellulose nanocrystals. This is also related to the nucleating effect. In fact, this nucleating effect, so of course, facilitate the nucleating step, meaning that we have more crystals, they form more easily, but sometimes the degree of crystallinity can be higher or it can be lower compared to the matrix. There is no direct relationship. Gas permeability. We can determine the water vapor permeability. So this is important, of course, for packaging. Water vapor permeability is the volume of water vapor which is exuded by a sample per unit thickness and unit surface during a given period of time under specified temperature, controlled relative humidity, and under a vapor pressure difference. The sample is here with some water. Water molecules pass through the sample, and you can determine the water vapor permeability using this equation. So delta M corresponds to the amount of gas that flows through the barrier. So delta T is the duration of the experiment, E is the thickness of the film, R is the area of the barrier of the film, and delta P is the difference in partial pressure across the barrier. It's also possible to determine the water vapor transmission rate. Both parameters are related, but it's not exactly the same thing. It corresponds to the quantity of water that penetrate in a sample of unit area and a defined thickness over 24 hours under controlled temperature and relative humidity under the effect of a water pressure difference. We can see that both terms are related, in fact. So this is just to show you an example in this material. So it's wine shoots reinforced PHBV, polyhydroxybutyrate hydroxyvalerate. Biocomposite, you have the water vapor permeability for the neat matrix and with different amounts of this natural, of this filler. So there are two data, virgin wine shoot filler or modified. So what we can see is, of course, when adding a hydrophilic filler, the water vapor permeability increases. Because PHBV is typically hydrophobic, you add a hydrophilic filler, of course, it's easier for moisture to penetrate into the sample. But we can see the effect of the surface treatment that limit the permeability of water vapor. Oxygen permeability, so again, it's important for packaging application. It is a material property that defines how easily oxygen molecules pass through a particular material. So it is defined by this equation, with V, the volume of gas permeating during a given time, E, the thickness of the film, R, the area of the film, again. Delta P is the difference in partial pressure across the barrier. And we can also determine the oxygen transmission rate, which is the volume of oxygen which penetrates through 1 square meter of a film over the period of a day under standard temperature and pressure. And it is given by this equation. Again, you can see that these two parameters are linked. So you can see that the unit is quite complicated. Sometimes this unit is used. The barrier. One barrier is equal to this. So this is just to show you what is expected for oxygen permeability. So when using fibers, or when adding fibers, and mainly nanofibers, what we expect is to have a tortuous path to limit the diffusion of the gas molecule. In fact, during this process, there are different steps that can be differentiated. The first one is the adsorption of the gas molecule by the sample. Then, dissolution. of the gas molecule, diffusion, and finally desorption. So these three steps occur in the sample. This is one example of, I don't remember what is this. Ah, yes. Oxygen permeability, sorry, it's film of pure microfibrillate cellulose or cellulose nanofibrils obtained from wood. In fact, good oxygen permeability is obtained with these cellulose nanofibrils, except when the relative humidity increases. You can see here, so this is a function of the film grammage, so the thickness of the film. The oxygen transmission rate decreases, but for a given thickness, when the relative humidity increases, you can see that the permeability increases a lot. Do you have any idea why? In fact, what is the reason to have a good barrier against oxygen? It's just because here we are considering thin cellulose nanofibrils, so meaning that we have a dense network of nanofibrils because of strong hydrogen bonding between the nanofibril. When adding water molecules, so at high relative humidity, it will compete with the interaction between the nanofibrils. And of course, so it means that we have a loose network, and in this condition, it's easier for oxygen molecules to penetrate. So, but this is a problem for cellulose. So it's a hydrophilic material, meaning that, of course, it's sensitive to water. One way to overcome this, but I think I already mentioned it briefly, is to use a film of cellulose nanofibril, for example, that provide the oxygen barrier properties, and to protect this film from moisture using another layer that can be wax, or it can be a hydrophobic polymer, and so on. So, some conclusion. The surface modification of, I'm really sorry, but why I have this? It looks like the previous conclusion. Maybe I copy and paste. Well, I don't know. Okay, maybe the second point. Polymer stiffness increases with the addition of fibers or nanoparticles, mainly when the adhesion with the matrix is good, but it is at the expense of ductility. The water uptake of the material increases when adding hydrophilic fibers, nanoparticles, but can be limited if the adhesion with the matrix is good. Dynamic mechanical analysis gives strong insight on the morphology of the biocomposite. You remember I discussed morphology recently, it's the arrangement between the phase. You remember the example I've given you. It was a blend of polystyrene and natural rubber. It's a two-phase material because the two polymers are immiscible. And you can see this from DSC experiment because you have two TGs. But you cannot say if natural rubber is the matrix or polystyrene is the matrix. From dynamic mechanical analysis, you can say that you have a two-phase system and you can identify the nature of the matrix. Okay? Fiber nanoparticles often act as nucleating agent for the matrix, and barrier properties can be improved when adding fibers or nanoparticles, but strong degradation is observed at high relative humidity level. Thank you. If you have any question.
Sir, that water uptake, you have shown the one equations in the slides.
Yes.
Where my question is, that equation is applicable only for biocomposites because, or is it like
So water
uptake?
vapor permeability.
Yeah.
Yeah.
Yeah, water uptake.
Yeah.
Not vapor.
And not this one.
Yeah, water uptake.
Yeah.
Yeah. Yeah.
Yes.
Yes. Yes. So this particular equation is being applicable only for biocomposite
No, no,
systems,
no, no.
or can be generalized for even.
It's even valid for a polymer matrix, not a
Okay.
composite.
Okay.
For polymers, just.
Okay.
But there is one restriction. You can see that here we have the thickness of the film. So it's necessary to have a film that is thin enough compared to the lateral dimension to have a one-dimension diffusion.
Okay.
Typically, the thickness should be lower than 1 millimeter, and you have to use 1 centimeter square sample.
Okay. So this can be practically also can be done now. We can take the initial weight and probably immerse it in water
Yeah?
and take out then see the how much is being absorbed.
Okay, this is the water uptake.
Yeah.
This is the water uptake.
Okay. From there you are calculating the thickness.
Here it's
Yeah.
to determine the coefficient of diffusion of
Okay.
water.
Okay. Okay. Perfect. So
Okay.
that's why it's applicable to all type of
Yeah.
composites.
Yes,
Okay.
yes.
So I was thinking that when it is biocomposite, especially for cellulose-based material, will have generally very high absorption. So
Yes.
where compared with other thermoplastics, the absorption will be lower. So whether does it make some limiting factor in these equations? That's
No.
Sir, in the slide number 13,
13 or 30?
1 3.
1, 3. Up. No. So this one. Yes.
Yeah, if you increase the strain rate, you have mentioned the modulus is increasing, right? In the second diagram.
Yes. The strain rate
So,
is the speed of elongation.
yeah, what would be the reason for that one?
What will be the?
What is the mechanism behind?
I can explain. First, maybe we can make a difference between the elongation rate and the strain rate. I define, so I remove it, but I define the strain. You remember, it's the logarithm of the actual length divided by the initial length. And we can derive this. In fact, the derivative of the strain, which is the strain rate, we can show this. It's given by this equation. This is the elongation rate, which is constant. But you can see that during the test, and because the length of the sample increases, the strain rate decreases. Now, what is the reason for this? There are two important parameters that need to be considered during this experiment. The first one is related to the material. When stretching a polymer, the macromolecule can deform easily or not. This refers to what is called the relaxation time. If the relaxation time is low, it means that the material, the chain can, or the macromolecule can easily move. If the relaxation time is high, it needs time to the macromolecules to move and to adapt to the stress which is applied. Okay? This is the time which is characteristic of the sample. Now there is another time which is characteristic of the experiment, which is the experimental time. If you stretch your material rapidly, the duration of the experiment is low, okay? Short. So meaning that the experimental time is short. If you stretch slowly, the duration of the experiment is longer, the experimental time is longer. You need to compare this experimental time and the relaxation time. If the relaxation time is lower than the experimental time, it means that the material can adapt to the stress which is applied. I mean that you stretch the sample, the material can deform. Now, if the relaxation time is longer than the experimental time, it means that during the experiment, the chain cannot deform. It means that when you stretch the sample, it breaks. The chain cannot deform. I don't know if it's clear.
Yeah, it's clear. Thank you. But will it be applicable for both amorphous and crystalline? This
This concerns mainly the amorphous phase.
amorphous.
Yes.
Okay.
For the crystalline phase, in fact, during a tensile test, it's another history. In fact, the crystalline domains can be viewed at different levels. The level of a single macromolecule, a level of a collection of macromolecules that form, which is called what is called the crystalline lattice, or the crystalline lamella, or the spherulite. And in fact, during a tensile test, the crystalline lamella will progressively break. And so at the end, we obtain what is called a mesomorphous structure. In the video, I show you that we have some filaments at the end of the test. It's because of this rupture of the crystalline lamella, because it was high-density polyethylene, so it's a semi-crystalline polymer. But the relaxation time is associated to the amorphous domains.
Sir, one more doubt regarding the DMA, dynamic mechanical analysis. You are saying it is stiffness we can calculate from there, but from the tensile test also we can calculate the stiffness, right?
Sorry?
In the tensile test, stiffness I am talking about
So
stiffness.
you did DMA or tensile test?
Yeah, which is more accurate? I am asking.
More accurate. It's not the same test. It is not the same test. Probably tensile test is more representative for the true life, let's say. Because usually a material is submitted to high stress, high strain, and it can break, and this is what we want to avoid in general. So it means that it's important to know in which condition the material will break to avoid it. Okay? This is for tensile test. Now for DMA, it's a little bit different. We can have other information than use or direct use properties. I mentioned previously that we can have access to the morphology of the sample. Of course, the morphology of the sample has an impact on the properties, but it's not the direct use properties. Another thing is that I showed you previously that in DMA, yes, in DMA here, we have a maximum in the damping factor. And remember that this damping factor is representative of the energy that can be absorbed by the samples, that can be dissipated. And so this is an information that we cannot obtain from tensile test. Okay? From this experiment, we know that, for example, if this curve has been obtained at 1 Hertz, we know that this material, when it is at 145 degrees, will a maximum absorption for frequencies of 1 Hertz. And so damping properties of polymer are important for many applications. So it means that I cannot say that DMA is better than tensile test. It's different information. Okay?
Thank you. Thank you.